In this lesson, we'll go over an informal definition for tangent lines and also talk about how to estimate their slopes. So to start with an informal definition, a tangent line to a given curve at some number x is equal to a is the line that touches the curve exactly once near that point, but is also moving in the direction of the curve. Let's try to make sense of this definition by looking at example 1. We have a curve, y is equal to x squared, and I'm going to choose a point P, 1, 1, that lies on this, which is right here. So here's the point 1, comma 1. There are a lot of lines, provided that you're near 1, that go through this curve only once. So for example, you could draw something like this. So I'll draw a line going like this. And as long as you're near x is equal to 1, it only goes through the curve at this one point. However, this is not a tangent line. So I'll just put not a tangent line. And the reason is there's a second part of our definition that says we have to move in the direction of the curve, and this thing definitely is not. What it means to move in the direction of the curve is if you're traveling on the curve itself, the direction is how it travels as you cross over this spot. So it's going like in this direction here. There's going to be exactly one tangent line, and I'm going to do my best to try to draw that in red. So I'll choose the point 1, 1, and this is more what the direction of the curve is. So it's this thing. So in red, we do have a tangent line. It goes through the point 1, 1, and it's moving in the direction of the curve. It only touches this one spot as long as we're near x is equal to 1, and that's it. So informally, we have this definition for a tangent line, and I tried to draw one here in red. Now the second thing is, what is the slope of this line? How can you figure it out? Here I have the formula for slope, and it depends on two different points if you'd like to use it. This question asks, can we find the slope of this tangent line by only using this point P, which is 1, 1? If you try to do this, if you try to only use the point 1, 1, which means x is 1 and y is 1, to figure out the slope, well, both x1, y1, x2, and y2 are all 1. So if you plug it into the formula, you get 1 minus 1 divided by 1 minus 1, which is 0 over 0, and you cannot divide by 0. If you type this into a calculator, you'll get an error message. So here we have division by 0 is not defined. And if you try to type this into a calculator, it's going to say error. So the issue is, I want to know the slope of the tangent line, but we really only know one point that falls on it for sure. So unfortunately, we can't just use this one point and this formula to figure out the slope. So what we can do, though, is try to estimate it, and we'll talk about that next. In example 2, I want to find several estimates for the slope of the tangent line to the curve y is equal to x squared at x is equal to 1. And the way we're going to do this is by using 2 points. So not just the point, I'll call it P1, comma 1, but also the point Q, which is x, comma x squared. The reason for this is, if you want to use the formula for slope, which is m is equal to y2 minus y1 over x2 minus x1, you have to have 2 different points. Now, just as a reference, here's the point 1, 1. This is the tangent line. I'll draw it in as a dashed line. It looks something like this. We need 2 points if I want to figure out the slope of this line. But what I'll do is I'm going to choose another x value to get a second point that I can plug into this formula. And I can choose any x value I want. So I think to start with, I'm going to let x equal 0. From here, I'm going to figure out what my point Q is equal to. I'm then going to take these 2 points, P and Q, and put them into this formula to get the slope. Okay, if x is 0, the y value is going to be 0 squared, which is also 0. So our point is 0, comma 0, like this. So here's a second point. This one's Q, and this one's P. And if you draw the line that goes between them, I get this thing. I can now use this formula to figure out the slope of this blue line. I think I'll let the point 0, 0 equal x1, y1, and I'll let the point 1, comma 1 equal x2, y2. If you compute the slope, it's y2 minus y1, which is 1 minus 0, over x2 minus x1, which is also 1 minus 0. And this simplifies to 1 over 1, and that actually is just the number 1. So here we go. Here's the slope of this line. It's 1. I don't know the slope of this line. But in some sense, the two slopes, this line and this line, are kind of close to each other. I mean, they're definitely not the same because I can see this is steeper than this. But 1 is a decent estimate for the slope of this line. The thing is, though, that we can do better. So I'd like to somehow maybe not use the number 0, but use a different number for x to hopefully get a better estimate for the slope of this line. Here's the trick. You want to choose a number that is close to 1. Try to visualize it. If you choose a number close to 1 and look at it on the curve and draw the line going between those 2 points, it'll be closer in slope to this line. The further the point moves away, the less close it will be. So I think what I'll do is, if I want a better estimate, how about I try this? Let's try this again, but I'm going to let x equal 0.9. So instead of letting x equal 0, I'll put x being 0.9 right here, which is really close to 1. The resulting line will have a slope that's closer to this thing. Okay, so if x is equal to 0.9, my point q is going to be 0.9, and if you square 0.9, you get 0.81. I'll let x1, y1 be the point 0.9, 0.81, and I'll again let x2, y2 represent the point 1, 1. In a calculator, if you compute the slope, y2 minus y1 is 1 minus 0.81, and then x2 minus x1 is 1 minus 0.9. If I type this into a calculator and carefully compute it, this reduces to 0.19 over 0.1, or simply 1.9. Let me try to draw this on here. It's going to be a little crowded, but if I choose a point close here to 1, and I draw the secant line that goes between it, so I get this, the slope of the red line, which is 1.9, it's pretty close to the slope of the red line. Now the question is, can we do better? Can we get a better estimate for the slope of the tangent line? And you can do this forever. I chose 0.9, but you can always go closer to 1 without equaling it. You could put another 9 at the end of this. So just to see what this looks like, why don't we try letting x equal 0.99. We're going to run out of room a little bit, but here I have q is going to be the point 0.99, and if I square that, I get 0.9801. I'll let x1, y1 be this point, that is, it's 0.99, comma 0.9801, and I'll let x2, y2 again be 1, 1. If I compute the slope, it's going to be y2 minus y1, that's 1 minus 0.9801, divided by 1 minus 0.99. I'm just going to directly type this into my calculator to see what we get. Okay, this time I get 1.99. Now, the slope of this line, which I won't even try to draw in here, it's even closer to the slope of the red tangent line. So here we go. We have 3 estimates. I had 1. It's kind of far away. 1.9 was better. And I think 1.99 is the best one that we have. Using these 3 estimates, could you make a guess as to what you think the exact value for the slope of the tangent line is? For me, if I was to make a guess, I would guess that the slope of the tangent line is 2. And the reason is, well, when I used 0.9, I got 1.9. When I used 0.99, I got 1.99. I'm guessing if I put another 9 at the end, it'll just put another 9 here. I encourage you to try that out, but if that were to happen, I think using 2 as the exact slope would be a very good guess. Example 3 is a lot like example 2. We're given a curve and a spot to estimate the slope of a tangent line, and we want to do this by using 2 points. So for starters, one of our points is going to be, well, x is equal to 3, and it'll have a corresponding y value. So we want to choose an x value that's close to 3. It's tempting to say 2, but if you try putting 2 into the function, you'll have 2 minus 2, and that will be division by 0. So I'm actually going to choose 2.5. 2.5 is relatively close to 3, and this will give us 2 separate points that we can put into the formula for slope. The formula for slope is m is equal to y2 minus y1 all over x2 minus x1. So we need the corresponding y values. So for 3, the corresponding y value is 3 over 2 minus 3, which is 3 over negative 1, which is negative 3. And for 2.5, the corresponding y value is 3 over 2 minus 2.5. That's negative a half in the denominator, so this is going to be equal to negative 6. It doesn't matter how you order these points, but maybe I'll call this x1 and this y1, therefore this is x2 and this is y2. And in the formula for slope, y2 minus y1, it's negative 3 minus a negative 6, all divided by x2 minus x1, which is 3 minus 2.5. And the slope here is going to be, okay, that's negative 3 plus 6, which is 3, all over 3 minus 2.5, which is 0.5. And here the slope, or at least the estimate, is 6. And I set it around to 6 decimal places. I mean, I guess technically you would put 6 zeros after, but I mean, you can just use 6. So here we go. 6 is the estimate that we have for the slope of the tangent line. But the point is, you can do better than this. The way you would do better is by choosing a number that is closer but not equal to 3. You know, I want to go over a way that kind of expedites this process so we don't have to do the same thing over and over again. Here's what I mean. If you want to use 2 points and the formula for slope, we already know that one of our points is going to be, well, x2 is 3 and y2 equals negative 3. Like, this will never change. You call this the point 3, negative 3. Now, your other point, you can actually just leave it as x1 is equal to x, and therefore y1 is equal to 3 over 2 minus x. The reason is for this, if you go to the formula for slope, it's equal to y2 minus y1, which is negative 3 minus, and then we can put the fraction 3 over 2 minus x, all divided by x2 minus x1, which is 3 minus x. You can actually enter this expression into your graphing calculator and then choose any number you want for x that is close to 3. So the way I would enter this into my calculator is, well, we have a fraction in the numerator. So here's my numerator. It's negative 3 minus, okay, I need another set of parentheses for the fraction. It'll be 3 divided by, but then I also need parentheses for the entire denominator of 2 minus x. So here's the numerator of this fraction, and we're dividing it by 3 minus x. Now I can go to a table of values and simply just choose a number x that's really close to 3 and not equal to 3, and on the other column, I'll have an estimate for the slope. So we already did 2.5, but if I type in 2.5, it does in fact give me 6. But we can do better. A better estimate would be if we try something like let's say 9. So here's 2.9. The estimate I get this time is 3. If I want 6 decimal places, that's 1, 2, 3, 4, 5, 6. So here's my estimate at 2.9. And it should be a better estimate. Can we do better? Sure. You could do 2.9 Let me try that. So if I type in 2.99, I get 3.030303. That's my estimate out to 6 decimal places. Great. Maybe I'll just do one more. I'll do 2.999. 2.999. And if I look at my estimate, I get 3.003003. These estimates should be getting better the closer this number gets to 3. Okay, at this point, I have several estimates. I think I'm ready to make a guess. I'm thinking the slope is probably 3. Again, you could say like, oh, maybe I'll put another 9 after that. If the numbers keep getting closer and closer to 3, it would seem like 3 would be a good guess for the slope of the tangent line. So why even consider the slope of a secant line or a tangent line? We'll see an application here in example 4. It says, suppose a ball is dropped from the top of Leaderly, and that Leaderly is about 210 feet tall. Using some basic properties from physics, you can derive this equation S of t, where S of t is the height of the ball above the ground after t seconds. Let's find the slopes of the secant lines over these 4 given intervals. And let's start with this one here in A. This is the interval from 0 to 2. And what this interval means is you're starting at t1 is equal to 0, and you're ending at t2 is equal to 2. And again, those are seconds. If you want to find the corresponding values in the function s of 0 is, according to this formula, 210. So by putting 0 in place of t, you're left with 210. Now, what is S of 2? I just typed this into my calculator, and I got 146. So again, these are seconds, and this is feet. So at 0 seconds, the ball is 210 feet above the ground, which is at the top of the building. But after 2 seconds, the ball has fallen, so now it's 146 feet above the ground. The slope over this interval is, I'll call it m, but it's going to be y2 minus y1 over, well, in this case, t2 minus t1. So I'll say, all right, that's really 146 minus 210, all divided by 2 minus 0. And I need to simplify this number. I get a negative value, but I get negative 32. But the point here is, well, negative 32 what? If you look at the numerator, this is feet and that's feet. And if you take the difference, the value that you get is feet. Here we have 2 seconds, and this is 0 seconds. And if you take the difference, you get divided by seconds. So this thing here has units of feet per second. And I'll denote it like this, feet per second. What this means is your function s itself tells you feet, the height of the ball above the ground. But this is now feet per second, which is a velocity. It's a rate of change. So anytime that you compute slope, in this case of a secant line, what you're doing is you're finding the rate of change of a given function. I would like to be a little bit more specific about this velocity. This is the velocity over an interval, and just to be a little bit more careful, this is an average velocity. So the average speed of the ball was 32 feet per second over the course of this 2-second interval, and the negative just means it was moving downward. So what's our application? If you find the slope of a secant line, you're finding a rate of change. And for a secant line, it's an average rate of change. Let's do this for part B. Okay, not from 0 to 2, but from 1 to 2. Here we're saying t1 is equal to 1 and t2 is equal to 2. If t1 equals 1, s of 1 is equal to, again, I can get this directly from my table, that's 194, and 2, it's still 146. If we want the slope over this interval, it'll be 146 minus 194, all divided by 2 minus 1. So I did this minus this over this minus this. If I compute this in my calculator, I get negative 48. But the units are still the same. In the top, we had feet. In the bottom, we had seconds. So the units at the very end are feet per second. So over this smaller interval, this was the average velocity. Again, here we had a secant line. All right, I'll try it again for this one here. Same idea. I'll define T1 and T2 and figure out the slope between those 2 points. Okay, so T1 equal to 1.5, I got that S of 1.5 was equal to 174. And again, here we have T2, it still is 2, and S of 2 is still equal to 146. When I compute the slope, M, that's going to be 146 minus 174, all divided by 2 minus 1.5. Again, I'm going to type this into my calculator to get the answer. Okay, the slope that I got was negative 56. Again, still we have feet over seconds. So this is negative 56 feet per second. And that, again, is an average velocity. And the reason it's an average velocity is because it was over an interval. Not quite enough room, but what I'll do is I'll do the work for this one down here. So for this last part for this thing, we have that T1 is 1.9, and the corresponding value of S at 1.9 is equal to 152.24. And again, T2 being 2 means that S of 2 is equal to 146. My slope M is equal to, let's see, I'll do 146 minus 152.24, all divided by 2 minus 1.9. And in my calculator, I get negative 62.4, and the units are still feet per second, which is still an average velocity. So here we go. We just found 4 average velocities, average because they happened over an interval of time. So if these are all average velocities, can we find how fast the ball is going at an exact moment? These were all over intervals, but what if I wanted to find the velocity at exactly the point 2? Here we can't really use these formulas to find the exact number because you would be dividing by 0. But maybe one of these is a very good estimate for how fast the ball is traveling at exactly 2 seconds. In fact, that's this one here. The smaller your interval gets, or the closer these two numbers are together, the closer you'll have an estimate for what we're going to call the instantaneous velocity at a given point. I'd like to state as a fact that if you're given a function y equals f of x, the slope of the secant line between a and b is what we call the average rate of change. And the slope of a tangent line at a given point is called the instantaneous rate of change. In the last example, we were finding average rates of change, and actually we found average velocities. We didn't actually find an instantaneous velocity, but we got a really good estimate for it. Down here in blue, I have a graph of the function s of t. So here s of t was equal to 210 minus 16 t squared. And that told us the height of a ball above the ground as it fell. Here in red is a secant line between t is equal to 0 and t is equal to 2. This is what we found in part A. We found the slope of this line. We found that it was negative 32 feet per second. That is the average speed of the ball over the interval between 0 and 2 seconds. Now here, this other line is what we figured out in part D. So for this one, when we computed the slope in part D, we got negative 62.4 feet per second. And that was on the interval from 1.9 to 2. Notice that this is very close to the actual tangent line at t is equal to 2. If you found the slope of the tangent line at 2, that would be the speed the ball was traveling at that exact moment. This is a very good estimate of it, and that's the best we could do with the formulas that we have. So just to put this all together, this is an average velocity, but it's a good estimate of the instantaneous velocity at 2. In example 5, we're told a student purchased an app that records the number of steps taken throughout a given day. And here in this table, it's the number of steps taken after 9 a.m. on the day a student went for a hike at a brook. So for example, at 0 minutes, there were no steps taken. After 10 minutes, there was 1,201, and so on. For part A, I want to find the slopes of the secant lines for these intervals, and I want to know what is the interpretation of these values. So in part A, if we look at the first part of this, the interval is from 0 to 40. So I want the slope of the secant line that goes between these points. This will be a very easy computation. And the reason for this is the corresponding y values are given. This one's 0, and this one is 3,384. Therefore, if we want the slope, it's going to be y2 minus y1. That's 3,384 minus 0, all over, in this case, t2 minus t1, which is 40 minus 0. So again, this is the y value, so this minus this. These are the t values. If you type this into your calculator, let's see what we get. Okay, I got 84.6. But the question is, 84.6 what? Well, the values in the numerator are steps, so the units up here are going to be steps. And down here, it's going to be minutes. As a fraction, this is steps per minute. The interpretation is, over this 40-minute interval, the student averaged 84.6 steps per minute. So this is an average rate of change. So let's make note of that. And this will be true for every part, for parts 2 and 3 of part A. When we compute the slope, it'll be the average number of steps taken per minute. So for the second part, same idea. Here, we're looking from 20 to 30, so that's the interval. The corresponding y values in steps are 2,307, and at 30, it's 3,102. So if you compute the slope, the difference of the number of steps is 3,102 minus 2,307, all over, that's 30 minutes minus 20 minutes. Again, going directly to a calculator, if we divide, we get 79.5, and that is steps per minute. And that's the average rate of change over the interval from 20 to 30 minutes. For the last part, here the interval is from 20 to 40. Corresponding y values are 2,307 and 3,384. The slope will be 3,384 minus 2,307 all over 40 minus 20. And here we have 53.85 steps per minute. For part B, it says, estimate the slope of the tangent line at 30 minutes, which is right here. And what is the interpretation of this value? For this question, we actually don't have a function to work with. We're only given a table of values. And this means actually getting the estimate can be quite difficult. One way you could do this is by graphing this on graph paper, drawing an equation that goes through it, and then using a ruler to draw a tangent line. I actually want to take a different approach. I'm going to say that this here, if you go around the value 30 and draw the secant line between 20 and 40, that would probably be a good estimate for the slope of the tangent line at exactly 30. So for part B, if I'm going to estimate the slope of the tangent line, I'll use 53.85 steps per minute. And what is the interpretation of this? This is an instantaneous rate of change. Meaning at exactly 30 minutes, the rate at which the students' steps were changing was 53.85 steps per minute. To maybe just more carefully justify this last part and why I'm using this estimate, I'll look at a graph of this table. Okay, so what we have here is a graph of the table of points in the previous example. And the last part of the problem was saying, can you find the slope of the tangent line at this one spot? If you try to draw in an equation between these points, it might look something like this. And the slope of your tangent line, I guess I'll put that in green, might look something like this. Like here's the slope of your tangent line. So the tangent line is in green. If you draw the line that goes between the point at 20 and the point at 40, it'll look something like this. So again, that is a secant line. Now, the slopes are probably different, but they're also relatively close. What this means is if you do not have a function to work with, but you just have a bunch of points, what you can do if you want to estimate, or the best you can do if you want to estimate the slope of a tangent line is by using points that surround a given point.